Hello everyone, I am Priya Karfa, the assistant professor of BSH in the Department of Mathematics. Today we are going to discuss the complex analysis portion, and this portion is that Cauchy Riemann sequences. Cauchy Riemann sequences are the most important part in this complex complex functions. So at first we know that what is the Cauchy Riemann sequences. Cauchy Riemann sequences are that Cauchy Riemann equations are ux equal to minus vy and vx equal to uy. What is ux, vy, vx, vy and uy? These are the partial derivatives. These are called partial derivatives. Ux is equal to del u by del x. That means this is differentiated with respect to x. Y is equals to del u by del y. This is differentiated with respect to y also. And similarly, vx is equals to del v del x. Last of all, vy is equals to del v del y. These are the partial derivatives should exist here. You know that. Then, in this example, what we want, we for the function defined by f of z equal to root over mod xy. Show that the Cauchy Riemann equations are satisfied at 0, 0. That means at the origin, but the function is not differentiable and analytic at that point. Here we apply the theorem. What is the theorem? Theorem is that Cauchy Riemann equation is satisfied, then the function is analytic. This is the necessary condition. And the sufficient condition is that the function is differentiable and analytic. The function is differentiable and analytic, then the Cauchy Riemann equations are satisfied. This is the necessary and sufficient condition. But here the sufficient condition is not true. So, as for the example, we take f of z equal to root over mod of xy and prove this theorem. So, now at first we satisfy the Cauchy Riemann equation. So, Cauchy Riemann, before we satisfy the Cauchy Riemann equation at the origin, at first we calculate the these four partial derivatives. So, let at first ux equal to limit z tends to 0 f of here x, so z, with respect to x, so here z tends to 0. And what is z? Z is an analytic function and it is the form, z is the complex functions and z is of the form x plus I y. So also f of z is equals to u of xy plus I v of xy. Here uxy and vxy are the real belongs to the real numbers. Here xy belongs to the real numbers, so uxy and vxy are the f of real numbers. That means functions of real numbers with respect to x and y. So here we apply the limit formula. Limit z tends to 0, f of z minus f of 0 divided by z minus 0. Here the function given f of z equal to root over mod of xy. So we write here limit z tends to 0, z f of z equal to root over mod xy and f of 0 equal to 0. So here we put z tends to 0. That means limit we expand x tends to 0, y tends to 0. Because z equal to x plus I y. So we divide x tends to 0 and y tends to 0. And here we put 0 minus 0 divided by z. So our result is 0. Then similar form we calculate uy is also 0, vx also 0 and Vy is also 0. So the conditions of Cauchy Riemann equations are Ux equal to minus Vy and Vx equal to equal. Then we get here Ux equal to is expressed that minus Vy, that means here 0 and equal to 0. So these are the equations, and Uy equal to Vx we get. So the first, so our questions, the first part is proved here. So Cauchy Riemann equations are satisfied at the origin. That means that is 0, 0 point. So our first part is proved. And the second part is the theorem portion, the sufficient condition. Sufficient condition is that the function is differentiable and analytic, then it should be Cauchy Riemann equations to satisfy. But here this is not true. The sufficient condition is not true. So we prove this. We prove that this portion. Take the example. So f of z equal to root over mod xy. So at first we calculate the differentiability. That means f dash 0. So f dash 0 limit formula is limit z tends to 0 f of z minus f of 0 divided by z minus 0. This is the limit formula f dash z. So here f of z is equals to limit z tends to 0 f of z is equals to root over mod of xy, and here z is equals to x plus iy. So here x plus iy. Now we take the path. This limit form we calculate. Now we take the path. The path is let y equal to mx, where m not equal to 0 be a path we choose for calculate this limit portion. Then we substitute as 0 equal to limit here y equal to mx. That means z is equals to x plus iy. So x tends to 0, y tends to 0. So here x tends to 0 only because we substitute y portion is mx. So x tends to 0 is equals to root over mod of y equal to mx. So m x's square, and here x plus ix, sorry, x plus I mx x plus I mx. Now we calculate this limit. Limit x tends to 0, root over mod m is constant and root over mod x square. So we apply the square root form x, and here x common 1 plus I m. Now we cancel out the x, and the form is limit x tends to 0, root over mod m divided by 1 plus I m. This is the which is different the values of m, which is the values of m is different. So we cannot get the unique values of the limit. So we cannot get the unique values of limit. So then we know that the limit exists only at the unique values. So here we cannot get the unique values because m values have m is, we take m is 1, then we get the another result m is equal to 2, then we get also the another result, so we cannot get the uniqueness. So the differentiable is not exist. The derivative is not exist. Derivative is not exist, and the derivative is not exist, so the function is not analytic, because the definition of analytic function is that at the point z equal to 0, it all neighborhood the function is differentiable. So here the derivative is not exist, so the function is not analytic. The function is not analytic at this point. Analytic at z equal to 0 point. So our question second part is also proved. The function is not differentiable and analytic